Welcome to this presentation on solvent-free organometallic migratory insertion reactions. Today we'll explore a fascinating area of green chemistry that combines organometallic reactivity with environmentally friendly approaches. Migratory insertion is a fundamental organometallic transformation where a ligand migrates to an adjacent coordinated unsaturated substrate, which is shown in Figure 2. Common examples include carbon monoxide insertion into metal alkyl bonds and the insertion of alkenes or alkynes into metal hydride or metal carbon bonds. This transformation serves as a key step in numerous cycles traditionally performed in organic solvents, such as the example seen in Figure 1. Moving to solvent-free conditions offers multiple benefits. First, there's a substantially lower environmental impact through elimination of hazardous waste streams and reduced carbon footprint. Safety is enhanced by removing flammability hazards and reducing exposure to toxic solvents. Resource efficiency improves dramatically through reduced material consumption and lower energy requirements. The process becomes more cost-effective by limiting solvent purchases and waste treatment expenses. Perhaps most importantly for synthetic applications, solvent-free conditions often deliver good product yields in shorter reaction times due to higher effective concentration of reactants and enhanced reaction rates, leading to improved atom economy. The reaction I'll be focusing on is a molybdenum catalyzed migratory insertion process. The starting reactant seen in Figure 3 is a classic organometallic compound containing a cyclopentadienyl ligand, 3 carbonyls, and a methyl group. The mechanism involves multiple equilibrium steps denoted by rate constants K1 and K3. In the first step, K1 and K2, a CO ligand dissociates, creating a vacant coordination site that's temporarily occupied by solvent. This step is critical as it creates the 16 electron species necessary for subsequent reactions. The next equilibrium, K3 and K4, involves displacement of the solvent by triphenylphosphine. Alternatively, the phosphine can directly coordinate to the complex after CO dissociates via the K5 and K6 pathway. The final step, K7 and K8, involves migratory insertion of CO onto the MO-ME bond, forming an acyl intermediate and creating the final product with a release of CO. Let's analyze the electron counting and oxidation states in this mechanism. Our initial complex compound exists as MO2 with a D4 configuration. It's an 18 electron species with the cyclopentadienyl contributing 5 electrons, 3 CO ligands contributing 6 electrons, and the methyl group contributing 3 electrons. After CO dissociation, the complex remains MO2 but becomes a 16 electron species, making it coordinatively unsaturated and is favorable for ligand association. When PPH3 coordinates, the complex returns to an 18 electron configuration while maintaining the MO2 oxidation state. Following migratory insertion of CO into the MO-ME bond, the oxidation state remains uncharged as the formal electron count is preserved. The driving force for this reaction includes electronic factors. PPH3 is a stronger sigma donor than CO, and steric conditions, as the insertion relieves crowding around the metal center. Additionally, the formation of the M to C acyl bond is thermodynamically favorable, providing energy to drive the reaction forward. The cyclopentadienyl ligand maintains E to 5 coordination throughout the reaction, donating 5 electrons to the molybdenum center and providing steric and electronic stabilization. CO ligands undergo significant bonding changes during the reaction. Initially, they form linear MCO arrangements as terminal carbonyls. After migratory insertion, the inserted CO forms an acyl group with a bent MCO arrangement and sp2 hybridization to carbon. This is accompanied by a weakening of the CO bond, observable as a lower stretching frequency in IR spectroscopy. The introduction of triphenylphosphine significantly impacts the electronic environment as a strong sigma donor but weak pi acceptor. PPH3 creates a more electron-rich metal center. Its trans influence weakens bonds opposite to it, facilitating subsequent transformations. Additionally, its steric bulk effects affects reactions kinetics by influencing the accessibility of the metal center. The transformation of the methyl ligand to an acyl group represents a fundamental change from a simple sigma bond with sp3 hybridization to a resonance stabilized structure with a partial double bond character between the metal and the carbon. Several analytical methods are crucial for monitoring this migratory insertion reaction. Solution IR spectroscopy, shown in Figure 4, is particularly valuable, allowing us to track CO stretching frequencies in the range of 1850 to 2050. The appearance of an acyl CO band around 1650 provides clear evidence of successful insertion. NMR spectroscopy, seen in Figure 5, offers a number of insights such as carbon NMR, which can distinguish between terminal CO ligands and acyl CO groups through dramatic chemical shift differences. 31P NMR provides sensitive probe PPH3 coordination to the metal center, while proton NMR monitors the changing environment of the methyl group during insertion.